In this next example, we'll look at graphing the curve r equals 1 plus sine theta. So we can approach it similar to how we approached the previous example, where we considered the angle theta as our independent variable and r as our dependent variable. So we can evaluate this function at different values of theta and then see what values of r correspond to that value of theta. One way that makes this easy, in my opinion, to do this more rapidly than plugging in individual points one at a time, is to think about the Cartesian equation y equals 1 plus sine theta, or I should say y equals 1 plus sine x, because we know how to graph this kind of function very rapidly. So this gives us a nice quick way of finding the values for r that correspond to a particular value of theta. So let's graph this Cartesian equation, and we'll use that to quickly get the values of theta, or the values of r and theta that go into our polar equation. So we know this is just the graph of sine x, and it's shifted up 1 unit. So it'll pass through the point here at 0, 1, and then at pi over 2 goes up to 2, and then at pi down to the middle, and then at 3 pi over 2 down to the bottom, and then at 2 pi back to the middle. Okay. So looking at these points here in the graph of sine x plus, or 1 plus sine x, we can quickly observe that here the values here along the x-axis are going to be the values of theta, and then the values here along the y-axis are going to be the values of r. So now we have a much more rapid way of picking out these values that we're going to put into our polar graph. But keep in mind, the polar graph is going to be different because the way that we're drawing the polar curve is now we're looking at the angle theta is going to correspond to these angles around the xy plane. So the angle 0 would correspond here with the positive x-axis. The angle pi over 2 would correspond here with the positive y-axis. The angle theta equals pi will correspond here with the negative x-axis. The angle 3 pi over 2 will correspond here with the negative y-axis, and then coming back to 2 pi brings us back to the angle here that we began at. So the points that I've plotted here essentially go through one complete rotation of this polar curve. Noticing that at the angle 0, we're going to start with an r value of 1. So let's start our graph there. So at the angle 0, which again corresponds here to the positive y-axis, we're going 1 away from the pole. As the polar curve goes to the angle of pi over 2, we're going to go to a bigger radius of 2. So here on the positive y-axis, we're going to go 2 out. So we can see there the point at pi over 2 is 2. Right, so we're a distance of 2 away from the pole. As we go from pi over 2 to pi, we're going to come back down to 1. So come back down to 1 here on the negative y-axis, negative x-axis. And then as it curves around to 3 pi over 2, then it's going to have a radius of 0. So it's going to hit the pole here at that angle. Okay, so let's kind of trace the trajectory that the curve is going to pass or trace through. So from 0 to pi over 2, right? We can look at this portion of the graph here. Is going to correspond to this section here in the first quadrant, right? Because we see that its radius goes from 1 here, and as the angle curves around to pi over 2, it's going to go to a radius of 2. right? Sort of like what we observe here. So this is again just a rapid way of getting plugging those points into our function r equals 1 plus sine theta. And then as it curves around here from pi over 2 to pi, we can imagine then this section of the graph there would go from 2 back down to 1. So it would look something like this. And then let's look at the next portion of the graph from pi to 3 pi over 2. It goes from a radius of 1 to a radius of 0. So we imagine it's going to curve in and it's going to hit the pole. And then finally for the last section here from 3 pi over 2 to 2 pi, it's going to go from the pole, from where the radius is 0, to a point where the radius is 1. So it completes it there. So we can kind of see how each of these little segments, or each of these little sections of the curve y equals 1 plus sine x, correspond to the polar curve r equals 1 plus sine theta. So in my opinion, this is going to be a helpful way of graphing a polar curve without necessarily having to plug in points. Okay, so we see here's our polar curve r equals 1 plus sine theta. By the way, this is called a cardioid, which also means heart-shaped graph. And so we can observe here why it's called a cardioid. It looks sort of like a heart, or an upside-down heart. How about the curve r equals cosine of 2 theta? So let's do something similar where we want to sketch the curve y equals cosine 2x for angles between 0 and 2 pi. In this case, you might notice that because it's 2x here, we're going to have 2 complete rotations of our cosine curve between 0 and 2 pi. For cosine, we know it starts at 1, and then passes through the points here, and that gives us 1 full cycle. Okay, so that would be from 0 to pi. It would give us 1 full cycle there. Because here, if we've got 2x here, we know the period is actually 2 pi over 2, which is pi. So there we've got our first period. Okay, but for our polar curve, we're going to go around 1 more full rotation to go all the way out to 2 pi. So again, it'll cycle through these values again. Okay, so there's our Cartesian version. So let's see how those values now correspond to the polar graph. In this case, we start with 1, 0 on the angle 0. We notice then from 0 to pi over 4, it's going to hit the pole at pi over 4. So that little section of the graph there, we can graph here between 0 and the angle pi over 4. Where it hits the pole. Okay, so we can imagine that this is going to form maybe one section of the graph before it hits the pole. Now the next piece here from pi over 4 to pi over 2, notice now is going to have a negative radius. So it's going to wind up, so going from pi over 4 to pi over 2, this section of the graph is actually going to wind up on the opposite side below here. And then it comes out to a value of -1 there, where it hits the angle at pi/2. Okay. And then as it sweeps around from pi/2 to pi, this would be 3 pi/4, is what I mean. It's going to head back to the pole. So here's the angle 3 pi/4. But again, we know that it's on the negative side for that portion of the graph. Okay, so between the angle pi/2 to 3 pi/4, we're actually going to graph it in this region below, because that's where the r value is negative. Notice it's below the x-axis for this graph, so it tells us the value of r is negative. Okay. And then again, as it sweeps around here from 3 pi/4 to pi, okay, it'll go from the pole from a radius of 0 to a radius of 1 at pi. So it's going to come out to a radius of 1 here at the angle pi. And then to complete it, we can imagine that it's going to cycle through these values one more time, and that'll complete the rest of the graph. So here I'll again just redraw this portion again in red. Now that's going to be going from pi to the 5 pi/4. The angle at 5 pi/4 here. And then from 5 pi/4 to 3 pi/2, it's going to be on the negative side. So it's going to be on the positive y-axis there for that portion of it. Oops, let me actually do that a little better. And then from 3 pi/2, so that would be the angle down here at 3 pi/2, but we're graphing it on the opposite side because it's on the negative side of the y-axis. And then finally for that last part there, from 3 pi/2 to 7 pi/4 here, that would be this angle here at 7 pi/4. It's going to return back to the pole. And then the last little section is going to complete the curve. So going from 7 pi/4 to 2 pi is going to complete the last part there. Okay, so hopefully now you can see how this curve is formed. We've cycled through the values here from 0 to 2 pi. And so we can look at the key angles that it hits from pi/4, pi/2, 3 pi/4, and so on, and plot those points here as it sweeps through those different angles. And again here, maybe it's going to be helpful to think of our Cartesian curve, y equals cosine 2x, as a way of rapidly getting those points on the curve r equals cosine 2 theta. And the shape of this curve is called a four-leaved rose. Okay. So this general type of curve is called a rose curve. But in this case, you can see it's got four petals, or 4 leaves. And one more thing we can consider when we're graphing polar equations is the symmetry that's displayed in the graph. So that in this case, we're considering 3 different types of symmetry. One is if a polar equation is unchanged when theta is replaced by negative theta, then we have a curve that is symmetric about the polar axis. And that would be symmetry with respect to the x-axis, essentially. Okay, so we see, yeah, we get the same r values when when theta is positive as we do when theta is negative. We get that kind of symmetry. You can observe that we had that in the previous example when we had our four-leaved rows. Another type of symmetry is if the equation is unchanged when r is replaced by negative r, or when theta is replaced by theta plus pi, the curve is symmetric about the pole. So that's more of a rotational symmetry, where if I were to rotate this curve 180 degrees, it's going to result in the same curve that we started with. And we see why that is. Here we've got the point at positive r comma theta is the same as the point at negative r comma theta. And we know that r theta and negative r theta are going to be 180 degrees apart from each other. And then finally, if the equation is unchanged when theta is replaced by pi minus theta, then the curve is symmetric with respect to the vertical line theta equals pi over 2. So this is more symmetry in the y-axis, where here we can see that the angle pi minus theta would be making an angle of theta with the negative x-axis, right? So if I have pi minus theta, that's really making an angle of theta over here. So if it's theta on this side, then this angle of theta would match it. And so that's how we get that kind of symmetry, if those two have the same r value when we substitute pi minus theta in for theta. Okay, so sometimes it can be helpful to consider the different types of symmetry that we might observe in a particular polar curve. And notice that in the previous example that we did with the four-leaved rows, it has actually all three of these types of symmetry. So you can verify that those three conditions satisfy that equation.